Hello, and I would like to perform a Kirchhoffs loop rule direct current problem where we have a circuit with multiple branches that has multiple EMF sources, in other words, multiple ideal batteries, and also multiple resistors. And there are, since there are multiple branches, there are also multiple electric currents in the circuit. So, in fact, we are going to try to find the electric currents in the following circuit. Now, this particular circuit has relatively straightforward numbers of 10 ohms, 20 ohms, and 40 ohms for R1, R2, and R3, the numbered resistors. This circuit also has current 1, current 2, and then current 3 already labeled for us, and then two voltages, voltage 1, voltage 2 of 10 volts and 20 volts. Also, direction of loops is indicated. Notice the direction of these loops, 1 and 2, seem to follow the directions of the currents somewhat, and that's usually a judicious choice. And notice the outside loop, 3, is also another possible loop. So, let us start with Kirchoff's junction rule. Okay? So Kirchoff's junction rule for electric currents. So remember, the junction rule tells us, just like the conservation of charge, but it's just the conservation of charge per unit time, that the currents should add up. That at junction point A, all the incoming current should equal the outgoing current. So I in equals I out, which in the notation we have, that should be I1 plus I2 is equal to I3. Okay? So that means the total current coming in equals the total current coming out. Okay, so that's one equation. So I'll label that equation 1. We might probably need to come back to that. Now let's talk about Kirchoff's loop rule. Okay, so now Kirchoff's loop rule is true as long as there are only conservative forces, namely we can define a unique voltage on each wire. And for that matter, when we are going across resistors and voltage sources, we can consider them like sinks and sources of voltage. So let's go ahead and start in the lower left corner and go clockwise for loop 1. Okay, so let's do loop 1, and we're going to say clockwise from lower left corner. So maybe sort of starting here, if you will, and going around this way. Okay, so I think we go across voltage 1. We go from negative to positive terminals. That's plus V1. And then we are still on a piece of wire, and then we go across resistor 2. But we go the correct direction because we're going with the current. Should be minus I1 R1. Then we hit junction point A. Then we come down across resistor 3 with the current. So we lose energy. That's minus I3 R3. And then we're still wire all the way back to where we started. So that should equal to 0. Okay, that's our second equation. Let's also do Kirchoff's loop rule, but now let's do it for loop, and let me write it over here, loop 2, that's going to be counterclockwise from the lower right So down here. So in some sense starting from here and then we're going counterclockwise. So I think we go across voltage 2. It's a positive. And then we go, still with current 2, we go across this resistor. And we go the correct direction because we're going with the current. So it should be minus I2 R2. Notice I2 R2, we're using Ohm's law. Then the last part should be exactly the same because we go across branch 3. So it should be minus I3 R3 equals 0. So that's a third equation. Okay. Now what we should do is we should write these equations in sort of a nice format to try to solve these. So here we have equation. So we have 3 linear equations. Equation 1, equation 2, and equation 3. So what I want to do is I want to write I1, then I2, then I3 with coefficients in that order. I want to put all constant terms on the other side. And I want to also fill in zeros when needed. So let's go back to equation 1, which was the junction rule. So I think it's going to be I1 plus I2 minus I3 equals 0. And by the way, there's implied ones here, if you like. Don't show a coefficient, it's just a coefficient of 1. How about 2? Equation 2. Well, it's minus I1 R1, but R1 was 10. So it should be minus 10 I1. And there's no I2, so plus 0 I2. And then we should have minus I3 R3, but R3 is 40. That's minus 40 I3 equals, now this voltage was positive. When it gets moved over to the other side of the equation, it becomes a negative. So it should be minus what V1 was. That should be minus 10. Lastly, equation 3 should be 0 for I1, because there's no mention of I1 in this equation. But then it's minus I2 R2, but R2 is 20 ohms. So that's minus 20 I2. And then we go across this resistor again, so minus 40 I3. And the voltage source here was voltage 2, which was a positive over here. It gets moved over to minus. That's minus 20. Okay. So what we can do is, if you like, you can write this down in a rectangular way, if you will. You can summarize all these coefficients in the following way, and we'll be able to solve this problem. Okay, so let's write the coefficients of each row and each column. So let's go 1, 1, negative 1. And then over here we have 0. And in fact, because there's an equal sign, I'll put a dashed line vertical here to kind of separate things out. Negative 10, 0, negative 40, and then negative 10, and then 0, and then negative 20, and then negative 40, and then negative 20. Okay, so what I've written down here is I've written down the coefficients of the linear system, and I've put them into a matrix. And I should be able to solve this matrix by reducing the matrix. It's just like solving 3 simultaneous linear equations. In fact, I will do this with the Texas Instruments calculator, and we should be able to get the currents I1, I2, and I3. So let's see how we can get those. Let's go to the calculator. So what we should do is we should, calculator on, clear. Let's go to second matrix. The first thing we need to do is we need to edit. So let's go over to matrix A and let's do edit. our matrix should be 3 by 4. How do I know that? Because this is 3 rows and 4 columns. So it's 3 rows, 4 columns. Okay, so that's 3 by 4. That's the convention. Well, with a 3 by 4 matrix, we should enter in all the coefficients. So I should type 1, enter, 1, enter, -1, enter, and then 0, enter. Then -10, enter, 0, enter, -40, enter, and then -10, enter. That takes care of the second row. And then finally the last row is 0, and then -20, and then -40, and then -20. Alright, so now that the data is entered, let's do second quit, and now let's do second matrix, and let's now go over to matrix math. So I want to scroll all the way down to the function RREF, which here is labeled as choice B, and that's short for reduced row echelon form. So I'm going to say let's perform reduced row echelon form, and let's go second matrix, and let's go to that matrix A, which is the matrix I want to perform this on. I'll close off the parenthesis, I'll hit enter, and then this should be our answers. And we should round these off. So notice that 1s on the main diagonal means I1, I2, and I3 are all solved for. So I1 is -0.143, -0.143. I2 is 0.429. So this is 0.429. And then lastly, I3 has the value of 0.286. So this is 0.286. All of these will have units of amperes. And then lastly, because I1 is negative, I1 actually goes the opposite direction. So really, I1 is going this way. So really, this is the true direction of I1. Like so. Now notice, what that really means is I1 again is in the opposite direction. And what that really means is, in reality, we had, notice I1 comes in here, that's I1, and combines with I3 to form I2. So what we should write is, we should write really I1 plus I3 equals I2. That's the real junction rule equation. But we didn't really know that because we didn't know the direction of I1. So again, this minus means opposite direction from what was originally labeled. And then let's put a box around these because these are our answers. Okay, hope that was helpful in solving this Kirchoff's junction rule and Kirchoff's loop rule. So in other words, a Kirchoff's laws problem to solve a resistor network of multiple EMF sources and multiple resistors for a DC setup. Thank you very much for your attention. Please smash that like button if you enjoy this content, and subscribe to the channel and to grow the channel. Please share this content with those in your sphere of influence. And I thank you for your attention, and I will see you in the next video.